So in this lesson, we're going to talk about optimization problems. And what we want to be able to do here is use calculus to find the optimal value of something in a given situation. So our optimum value is always going to be a maximum or a minimum point of some quantity in our question. And this quantity always has to be maximized or minimized subject to some constraints that are given inside the problem. Okay? And it's figuring out what exactly the quantity is and how exactly to express those constraints mathematically, which makes these kinds of problems a little bit tricky. So there is a general process that we are going to follow in optimization problems. This is almost straight out of your textbook, page 305. And really, a lot of this stuff is just general problem solving stuff. First off, we want to try to understand the problem. Now, when we try to understand the problem, we're going to be doing some specific things. We might draw a diagram, we might list the given information, the relationships between the given information. The key one that we are going to do that we haven't done before is identify the quantity to be optimized. Always in these questions, there's going to be something that we're trying to make as big as possible or as small as possible. Okay? And we are going to want to choose specific variables to represent the variables that we have based on what we want to be optimizing here. Step 2, once we have understood the problem, we want to figure out a function that represents this quantity to be optimized. Okay? And we have to express it in terms of one variable. So after step 1, we're probably going to have 2 variables in our problem. We need to use one of these relationships between our variables to get ourselves a function of one variable. And as we're doing this, we'll check the domain of the function as well. Once we have our function, we can go ahead and find our maximum or minimum value using the techniques that we've been using all along here. We're going to take the derivative, find our critical numbers, make sure that they're in the domain, and we can use the second derivative test that we just talked about to verify that this thing is either a maximum or a minimum value. And then finally, we go back and we take a look at the original question and make sure that the numbers that we have calculated or the values that we have calculated actually answer the question that we wanted to answer. So we'll do 2 examples, I think, here in class, and there's a couple other ones that are posted on the website already. So here is, well, this is example number 2. Number 1 is already posted. This is a problem you actually did back in grade 9. Okay? A farmer has 800 meters of fencing and wished to enclose the tenses don't agree there, sorry about that, and wishes to enclose a rectangular field. One side of the field is against a country road, which is already fenced. What are the dimensions of the field with the largest area? So first thing we probably want to do is draw a diagram, figure out what this question is all about. So we've got our road coming along here like this. We want to make a rectangular field that borders our road kind of like that. And what are we trying to optimize in this question? What are we trying to either make as big as possible or as small as possible? Malcolm? And by size, what sort of, how would we measure the size of the field? Like, what quantity means size in this case? The area of the field, right? So it's area that we are trying to optimize. So we are going to need to get an expression or a function for the area of our field if we are going to optimize. Okay? So if we're trying to calculate the area, the variables we should probably use, well, if it's a rectangle, we know that the area is going to be length times width. So I'm going to introduce these variables here for the length and the width and the width. So this thing is fenced on all 3 sides. Now, this function here for the area, the quantity that we're trying to optimize, has got 2 variables in it. It's got length and it's got width. We need another relationship between length and width that we can use so that this function only has one variable in it. So how else do we know that the length and the width are related to one another? Let's go back to the question. Look, have they given us any information that we haven't used yet? Marine. Yeah, we've got this 800 meters of fencing that we haven't used. So we know that if we're going to use all of that 800 meters, we've got a fence around these three sides here, right? So we can take that 800 meters, and that is going to give us one of our widths, one of our lengths, and one of our widths. Okay. Kind of like the perimeter here. So 2 widths plus 1 length have to add up to 800 meters. Now, we can take this expression that we have here, 800 equals 2w plus L, and we can rearrange it for one of our variables. Okay? And then once we have it rearranged for one of our variables, we can sub it down here into our area expression, and then we'll have a function of a single variable. Make sense? Okay. So should we rearrange it for length, or should we rearrange it for width? What do you think? Why width? 2 width is just the length? Well, what I'm saying here is we can rearrange this 2 ways. If I solve this thing for width, I'm going to get width equals 800 minus L over 2. And if I solve it for length, I get length equals 800 minus 2w. Okay? I'm going to take one of these expressions, sub it into my area equation, and that's going to give me the function that I'm going to work with. Which one is easier to work with, the w or the L expression there? Or does it matter? Why L? No fractions. Yeah, we want to avoid that fraction if at all possible. Okay? So we can take that L expression and sub it in here for L. L is 800 minus 2w all times w. So now we have an expression for the area which only depends on a single variable, and that's w there. Now, are there any restrictions that we can place on our variables length and width here? Okay, is our domain restricted at all? Is there sort of a maximum or a minimum value that width and length can have? Well, there's certainly a minimum value that they can have. If they've got to be greater than 0, right? We can't have a negative width and we can't have a negative length. Is there a maximum possible value that they could have? 800. Yeah, 800 for sure for the length. Because if I make this side up here 800, then I've used all of my available fencing for the length, and there's none of it left for the width. In terms of the width, my restriction is a little stronger. Width has to be less than 400 because I need to have 2 widths in my expression here. Okay, so if I make one of my widths 400, the other one has to be 400 as well. That would take up my 800 meters of fencing right away. All right, so we've got our function. This is actually the hard part, is getting to this function. Okay? Once we've got this function, this is just stuff that we've been doing all along in the course. Okay? We want to take the derivative of this, set it equal to 0, solve for our critical numbers. So what I would do is I would simplify this a little bit by expanding it. So multiply each term inside by that w to get 800w minus 2w squared. And now I'm going to take my derivative. Okay. A primed is 800 minus 4w. Set this equal to 0, and I'm going to solve for w. So w is 200. Now let's say I wasn't sure whether this represented a maximum value or a minimum value. What I could do then is I could use the second derivative test to verify this. So I could just come over here and I could say, well, my second derivative is going to be the derivative of a primed here. So if I take the derivative of a primed, I get negative 4. Negative 4 is clearly less than 0. So the second derivative test is telling me that this value, w equals 200, corresponds to a local maximum. Was that what I was looking for in this question? Let's scroll back up. What are the dimensions of the field with the largest area? Yeah, so I wanted to maximize it. I found my local maximum. Am I done? Well, in the question it was asking me what are the dimensions of the field with the largest area. So I need full dimensions here. So I need to figure out my length as well. Fortunately, I've got a little equation over here that gives me the length in terms of the width. So my length is going to be 800 minus 2w, which is going to be 800 minus 2 times 200, which is going to be 400. So sum it all up. Largest field is when our length is 400 meters and width is 200 meters. So to optimize the area of the field, or make it as large as possible, we have to make our length twice as big as our width, which is the exact same answer that you got back in grade 9 when you did this problem. Only back in grade 9 you set up a table and you calculated all the possible values of length and all the possible values of width, and you calculated the area and you looked at what you had. A little easier with calculus here.